thank everybody for being here this afternoon. Our new strategic plan places a significant emphasis on climate change work in the agency. So to ensure that we're able to meet those goals and do it in a way that's cohesive, where we're cooperating and understanding sort of where the science is with regard to climate change in our region, we have set up a 10-month speaker series where we're bringing leading experts from across the region to the agency to provide information on the latest and greatest with regard to climate change science. We're really fortunate in Washington State to have at the University of Washington the Climate Impacts Group, who are doing some of the most progressive research into climate change in the country, if not in the world at this point. So many of our speakers we are very fortunate to have on our agenda. As part of the state's method or activities with regard to climate change, we're also participating, DNR, in the development of a statewide climate change adaptation strategy. The hope through these presentations is that when we start to look internal and develop our internal strategy, that it's both compliant with the state strategy, and everyone who will be participating in its development will have access to the same information that this statewide group has. So that's sort of a little bit of the background on the history of the speaker series. I really do appreciate everyone being here today. Today we have Lara Whitely Binder from the University of Washington Climate Impacts Group. Lara is an outreach specialist at the UW. She assists the Climate Impacts Group with its efforts to disseminate information to decision makers on the impacts of climate variability and climate change on the Pacific Northwest, and to support decision makers in the use of this information. She earned her master's degree in public affairs at the University of Washington's Evans School of Public Affairs in 2002. Prior to attending graduate school, Lara served as groundwater protection coordinator for a consortium of public and private groundwater suppliers in the greater Cincinnati, Ohio metropolitan area. As a coordinator, Lara developed and administered a multi-jurisdictional groundwater protection program. She's going to talk today about the broader impacts that we can expect to see in the Pacific Northwest from climate change. And with that, please welcome Lara. Thank you.
So as Rachel mentioned, this is really an overview, and through the different speakers you're going to have over the next 9 or 10 months, you'll be able to have an opportunity to get into any of these topics or others in more depth. But I'm happy to obviously take any questions as we go along the way. Feel free to interrupt. So as Rachel mentioned, I work with the Climate Impacts Group at the University of Washington, and we have been doing research over the last 15 years on the impacts of natural climate variability and climate change on the Pacific Northwest environment. And it's human systems and its natural systems. And we do this through a variety of mechanisms, doing research and applying different methodologies for downscaling global climate data to the regional scale, through water or hydraulic modeling and impacts assessments to water resources, terrestrial systems, aquatic ecosystems, and then through support for adaptation planning and also through outreach. The goal of this work is to provide scientific information to the decision-making communities as yourself, and to provide this information in a way that can actually be used. What we try to avoid is what we call what's often called the loading dock approach to science, where you just kind of do the science, you stick it out there, and you just assume it'll be used, everybody will understand it, and somehow it will provide some benefit. Instead, we try to work more closely with the decision-making community to make sure that the science is meeting their needs, that we're addressing questions that they have, and to do interesting research at that as well. Ultimately, the goal of all this work is to help the region become more resilient to the impacts of climate variability and climate change. I apologize if I'm blocking your view here. So I just want to spend a few minutes talking about what's projected at the global scale as a way of setting the stage for what we expect at in the Northwest. So human activities have increased the concentration of major greenhouse gases since 1750. And it's not a problem that we have greenhouse gases in the atmosphere. These are a natural component of our atmosphere. They comprise less than 1% of the total atmosphere. But and without these greenhouse gases, Earth's average global temperature would be around 0 degrees Fahrenheit. So it's not a problem that we have greenhouse gases. The problem that we have is that through human activities, such as burning of fossil fuels and through major landscape changes, we've enhanced the concentration of greenhouse gases in the atmosphere in ways that are basically outpacing the natural cycle of these gases. So it's similar to having food, right? The problem is not that we have food. The problem is that we often eat too much of the food. So it's kind of like that. So if we look at how, well, the IPCC, I should say, has looked at how these greenhouse gases have changed over the last 250 years. And let me take a step back to say the IPCC is the Intergovernmental Panel on Climate Change, which every 6 years or so releases a major synthesis report integrating the science on climate change and helping to basically consolidate what we know and what we don't know about climate change, climate impacts, and also mitigation strategies or mitigation needs. So the IPCC has looked at, and research has looked at how greenhouse gases have changed in the last 250 years or so, and carbon dioxide has increased about 35% since 1750. The way to look at this figure is showing the change in carbon dioxide from present day going back 10,000 years. And as you can see, of course, there have been variations over time, but it's this last 250 years or so, which is magnified here, where you see this dramatic increase in the atmospheric concentration of carbon dioxide. 1750 is considered the start of the Industrial Revolution, where we started really intensively using coal and other fossil fuels as energy sources. We look at some of the other greenhouse gases. This is methane, which has increased 142% since about 1750. Same figure, present day, going back 10,000 years. Again, you see this huge spike in the last 250 years or so. And then looking at nitrous oxide, that has increased about 18%. Now, looking forward over the course of this century, the IPCC projects about a likely range of warming of 2 to 11.5 degrees Fahrenheit. This means that there's, based on all the model output that they've looked at, there is a greater than 66% chance that by the end of the century, the amount of warming that an average global temperature that we will have observed at that time will be somewhere between 2 and 11.5 degrees Fahrenheit. Within that is what they call their best estimate range, which is actually 3.2 to 7.2 degrees Fahrenheit. So this is a subset of this larger range. The IPCC is projecting a range of temperatures rather than, is that not clear?
Or me.
Yeah.
Oh, no, I'm fine.
Okay, that's fine. This is actually,
I just went.
No, okay, that's fine. Actually, this is the first time I've actually presented this slide this way. So I was thinking, maybe I'm off in how I'm presenting it. But what I'm trying to just show, is the general range and then the subset. But the global projections are presented as a range rather than a single value because there are different assumptions that go into these projections. So to model these global temperatures, you have to model future greenhouse gas emissions and what those concentrations will be in the atmosphere. And that's going to depend on how global population is going to change, how our energy sources are going to change, and how our economies integrate. There's a long list of variables that they look at and make different assumptions about to kind of play these what-if scenarios. And so that is why you wind up with a range, because no one scenario is considered more likely than the other. So, for example, at the low end here, the B1 range, that's assuming global population peaks about at 9 billion mid-century, and it assumes that we rapidly move to greener energy technologies. As a result of that, you get lower greenhouse gas emissions, lower concentrations in the atmosphere, and from that, lower rates of warming. At the other end of that, under the A2 scenario, you have high population growth. I think it peaks out around 11 billion people. You have continued reliance on fossil fuels. So as a result, you have higher greenhouse gas emissions as you move through the century, and from that, higher rates of warming. Now, this warming will be neither uniform spatially, and it will not be monotonic, meaning that we won't see one warm year after the other, where each year gets successively warmer. We will see variations. We will see years that are cooler than the previous year or cooler than average. We will see years that are warmer than average. What's happening, though, over the long term, over the course of the century, is that average to which everything's being compared to is progressively getting warmer. This is looking at the spatial distribution of warming under the A2 scenario, which was that more, that upper warming or more aggressive warming scenario. And what you see, this is 2020 to 2029, and then later in the century, what you see is more warming over land areas than over the ocean. And that's because it takes more energy to heat up the ocean, to heat up the water. And more warming in the northern latitudes, far northern latitudes. And this is in degrees Celsius. I should convert that to Fahrenheit, but much more warming in the northern latitudes than, say, even the tropics. But significant warming overall globally.
Why do you think it's polar like that?
Pardon?
Why do you think it's polarized?
There are various theories as to what may be driving that. One is the ice albedo feedback and the lack thereof. So as you get warming and you get more snow and ice melting from the polar regions, you expose more dark land surface, and that in turn absorbs more heat and radiates back heat. So this is, of course, relative to probably 1970 to 1999. So compared to how much snow and ice there is now versus how much there would be in the future, you would just have more heat trapping capacity, more heat absorbing capacity. Could also be a function of polar winds and how heat gets distributed up there. But the leading expectation of what's driving this is that ice albedo feedback and the loss of that feedback over time. Of course, what's happening globally is interesting, but now we need to bring it down to the scale of the Northwest. And what the Climate Impacts Group did in the most recent, or in the first Washington Climate Impacts Assessment, which was completed in 2009, is we looked at two emission scenarios. We looked at the B1 emission scenario, which I described earlier, which involves less warming because of lower population growth and more rapid integration of green energy technologies. And then we used a medium emissions growth, A1B, which actually at mid-century is one of the more aggressive warming scenarios. So, what is more aggressive warming versus less aggressive warming really depends on what time you look at, because these scenarios crisscross each other throughout the course of the 21st century. What we find is that all the scenarios that we looked at, looking at 20 model runs, two emission scenarios, so essentially there were 39 because one model didn't use one of the emission scenarios. Anyway, 39 modeling scenarios, we find all of the scenarios agree that there will be warming in the Northwest over the course of the 21st century. Exactly how much warming will depend on which model and which scenario you're looking at. But when we aggregate those, we expect to see warming on the order of about 2 degrees Fahrenheit by the decade of the 2020s, about 3 degrees Fahrenheit, 3.2 degrees Fahrenheit by the decade of the 4040s, and about 5 degrees Fahrenheit by the decade of the 2080s. These smaller values underneath are the low and the high end of the ranges associated with those time periods. This blue line here is the 1970 to 1999 average. And what we see is that in the course of the 21st century, even at the low end of the projections, we are likely to see warming that exceeds anything that's been observed in the 20th century in terms of the changes in our average annual temperatures. And we are expecting warming across all seasons, with the most significant warming during the summer months. Changes in precipitation are much more difficult to tease out, and that's because of two things. It is very difficult to model precipitation both globally and regionally, because of challenges in modeling cloud formation, and then also because of the wide range of natural variability that we have in the Northwest. So that makes it difficult to tell how climate change may be pushing averages. When you consider before with temperature, the trend was well above that 1970 to 1999 average. Here's this 1970 to 1999 average on that zero line, and really we don't see much of a change. And what we're expecting on an annual basis is an increase only of about 1 to 2% by mid-century, maybe as high as 4% by the 2080s, but with an enhancement of the seasonal cycles. So most models agree that we would likely see wetter winters and drier summers. There are models that produce drier winters and wetter summers. There's much less confidence about the precipitation projections than the temperature trends because of the difficulties modeling precipitation. But at this point, we do expect wetter winters, drier summer with minimal changes in overall annual precipitation. whether that rain comes, that increased winter precipitation comes as a steady drizzle or comes as those kind of pineapple expresses that tend to cause a lot of flooding problems is a big question. And obviously from a management standpoint, it has the two scenarios of very different implications. So what can we say about extreme events? Well, extreme events are a challenge because there aren't that many of them, so it's very hard to test statistical significance. But we have seen actually few statistically significant changes in extreme events over the last 50 years, although it's interesting because you talk to most folks who deal with stormwater management, and they get the sense that the intensity of events has been increasing. And this may be the case indeed, but when you look at a statistical significance test, we don't see anything that is significant, except possibly in the Puget Sound region. And what that statistical significance test is telling us is, would we expect to see these types of extreme events just given the range of natural variability, or is this indeed something that would exceed what we would normally see? And so, yeah.
Do you have land use cover changes in that model?
These are, in this work, no. No, these are based on the use of a regional climate model. So there has been some work in the Puget Sound region, independent of this, by Longquo, looking at land use changes and runoff, changes in runoff, streamflow runoff in the region. But in terms of the intensity of events and what the statistics of the precipitation, how much is falling within a certain period of time, that does not take into account the land use changes. Looking forward in time, through the use of a regional climate model running two scenarios, we find that we could see some changes in more extreme events with more intense precipitation events happening in the future. The results are very highly varied, and the spatial distribution is highly varied as well. So it's a very murky picture. I realize it'd be nice to have a real clean, crisp, clean answer that yes, we will have more extreme events, or no, we won't. But we do, at least at this point, anticipate some increase in extreme events, but we still have to, the signal for that is not as robust as we would like at this point. So what do changes in temperature and precipitation mean for Northwest hydrology? We do expect that the changes in temperature and precipitation are going to transform the hydraulic behavior of many mountain watersheds, and by this we are referring particularly to patterns of runoff, which I'll get to in a moment. A key impact is the loss in April 1st snow cover. So we look at April 1st snow cover because it is an important measuring date for water supply, and it's a data set, it's a time period for which there are lots of data measurements for looking at how snow in the past has responded to changes in temperature. And what we see is because of, through the modeling, what we see is because of warmer winter temperatures, less winter precipitation is falling as snow, and more of it is falling as rain. This is particularly true in your low and mid-elevation basins, which already sit close to the freezing threshold for long periods of the winter season, so that when you get another 1 or 2 or 3 degrees of winter warming, it bumps those basins up above freezing for longer periods of time, and that's what's contributing to this shift in the type of precipitation that's falling. You also see, because of warmer springs, we see earlier snow melt from these watersheds. So looking at the two scenarios, we see losses in the range of 27 to 29% by the 2020s, looking out further in the 2080s, losses in the order of about 60%. And we can break this information down by elevation band through the use of the models. So again, it's these mid and low elevation basins that are most sensitive. So what do we mean by that? Low elevation are the basins typically lower than 3,000 feet, mid elevation in that range of 3,000 to 6,000 feet. And as you can see, as you go higher, the decline in snowpack is less, but that's just because those areas still remain fairly cold throughout the course of the winter season. Now, losses in snowpack and the changes in temperature and precipitation will have an effect on stream flow. These are hydrographs for 3 different types of basins, 3 different types of watersheds that are very, 3 different categories of watersheds, let me phrase it that way. The first is a transient or a mixed rain-snow basin. The second is a rain-dominant basin, and the third is a snowmelt dominant. And of course, but being a hydrograph, these are starting in October, ending in September, because that's how water managers like to break out the water year. So what I'd like to show you is just, if I could just draw your attention to this black line here, which is the historic runoff in the Yakima, versus the red line, which is the change in the runoff by the 2080s. And what you see is, because of the warmer winter temperatures, we see more precipitation falling in the Yakima as rain, resulting in higher winter stream flows. And because of the lack of snow that is in the basin as a result of these warming temperatures, essentially no spring peak, no peak spring runoff. Whereas presently what happens is you get some increase in fall stream flows with the rain, snow starts accumulating, so stream flows drop, then you get the big spring pulse as the snowpack melts. So you see a shift in this basin type from one that has a two-peak hydrograph to one that is single peak with most of the water coming off in the winter. For the Chehalis River, which is a rain-dominant system, there's essentially very little to no snow in the basin, so you don't see really much impact at all in that type of a basin, except for the potential increase in winter precipitation. So you do see a slight bump in winter runoff in the basin, and a slight decrease here in the summer because of the increased evaporation associated with warmer summer temperatures. And then in the Columbia River at the Dalles, which is a snow-dominant basin, but really integrating lots of basin types, what you see is a slight increase in fall and early winter stream flows as a result of more winter rain falling as rain rather than snow, or more winter precip falling as rain rather than snow, and decreased peak runoff in the spring because of the lower snowpack. So as you can see from these figures, it's these transient, these mid-elevation basins that are really the most sensitive to the warming, again, because those winter temperatures are already fairly close to freezing. These shifts, as I mentioned, between rain-dominant and snow-dominant and your transient basins are potentially significant. If we look historically, we have a mix of rain-dominant, which are the green basins, snow-dominant, which are the red, and, I'm sorry, transient basins, which are the red, and blue, which are the snow-dominant. But with the warming that's projected and with the changes in snowpack and runoff, what we see through the course of the 21st century is a gradual shift to virtually no snow-dominant basins by the 2080s, by the end of the 21st century, under both scenarios. And actually, we've done this mapping for the Columbia Basin as a whole, and Oregon becomes all rain dominant by the 2080s. There are not even any transient basins in Oregon. And then this Idaho loses either all or most of its snow dominant and looks a lot more like Washington with this combination of largely rain and some transient basins. That obviously has implications for management of water resources in terms of the timing of runoff and implications for flood control and other things which I will get into shortly. So what does this mean for aquatic and terrestrial systems? Because of the projected increases in winter precipitation and because of the warming, which is shifting more of this precipitation to rain rather than snow, we do expect to see more winter flooding, particularly in basins on the west side of the Cascades. If it's a basin that typically floods in November and December now, that's a good marker of a basin that's likely to see an increased flooding risk over time. This is looking at these changes in flood statistics that was done in the salmon chapter from the Washington assessment. And what you see by the 2080s in many basins in the Cascades are increases in flood risk up to 70% on an annual basis. Of course, this has implications for sediment transport and erosion. Has implications for flood management in your urban areas, or at least where you have the kind of the urban-rural interface, like up in Skagit and other parts of the South Puget Sound region. And it has implications for salmon and salmon reds, and with the potential for stream bed scouring events. Looking on the summer months and the implications on water temperature, we see implications for salmon there as well. So what this figure is showing, this is also from the Washington assessment, are changes or historical air temperatures. The big blobs are the average air temperature. The specific dots are stream flow locations that were examined in the Washington assessment. And the color matches is down here. This is the scale for the color. So what we see, obviously, are the cooler western Washington, warmer interior, and different stream flow temperatures at various spots. By the 2040s, under the A1B scenario, we see much broader warming in the interior basin, interior Columbia River Basin, and much more warming over in western Washington as well. Yellows are temperatures that are stressful for salmon. The pinks and reds are temperatures that are moving into fatal for salmon, depending on individual salmon species and stocks and whatnot. So what we see through this work is that in the interior Columbia Basin, we have large areas that are in August on any given year are potentially going to have temperatures that are fatal for salmon using the streams at that time. That doesn't mean that there are not going to be any salmon in those systems at all. It just means that for the salmon that are in those systems in August, they're going to be facing more extreme conditions and more stressful and potentially fatal conditions, particularly for if they're at life stages that are sensitive to those temperatures. And it's important to note that while this is kind of the obvious one, we do expect to see more of these stressful conditions in western Washington. But as I mentioned, the impact's really going to depend on the particular salmon and its life history type and where it's at any particular point in time. So we're look at the summer conditions, the low flows and warmer water. Those are going to create problems for species such as Columbia Basin sockeye, summer steelhead, summer chinook, Lake Washington sockeye and chinook. The winter flooding, increased winter flooding, the Puget Sound Basin creates problems for steelhead, coho, and stream-type chinook, just as an example of some of the individual stocks that could be affected by these impacts. Impacts on Pacific Northwest forests are varied, of course. Forests on the east sides of the mountains are going to be most sensitive to the warming temperatures and the increased drought conditions that are projected. But forests on the west side will also face increasing challenges, particularly with changes in disturbance from insects or disease. And there we do expect to see an increased fire risk on the west side of the Cascades as well, although not as acute as on the east side. Of course, we have a lot more fuels to burn over here, so I guess it's still going to be an interesting situation. But in effectively, the stress complexes, things like fire and insects, are expected to be the dominant changers of the game in the course of the 21st century. So because of the warmer, drier conditions, more trees are under stress. That makes them vulnerable to things like the mountain pine beetle, which are expected to increase their range as a result of climate change. But then other insects and other diseases as well that may benefit from climate changes could also take advantage of the vulnerable trees. And of course, once we have large stands of ill or dead trees, that increases the fire risk. We also expect to see changes in productivity, particularly that's elevation dependent. So trees that are up at the top of the snow line or at the top of the tree line actually benefit as a result of climate change because of lower snowpack and warmer spring temperatures. You get a lengthening of the growing season up at the top of the tree line. So you would see more tree growth, more productivity at the top of the snow line or top of the tree line, whereas at the southern end, at the bottom, because of the warmer conditions and the increased soil moisture deficits, we actually see decreased productivity at that end. We also expect to see shifts in the distribution of species, and I'll have a few slides to exemplify that. So if we look at the current climate suitability for Douglas fir and how that might change by the 2060s, we see that more areas of Washington State become less climatically suitable for seedling establishment for Doug fir. So what this is showing you, the orange is showing you areas where less than 50% of the models agree that that will be a good area for Douglas fir. So you could consider this as almost an indicator of the contraction of the range. But again, it doesn't mean that there will be no Douglas fir, for example, here. It just means that the conditions will be less suitable for establishment. So where there is disturbance, it may be more difficult for seedlings, Doug fir seedlings, to get reestablished in those areas. Similarly, for lodgepole pine, if we look at current climate in the areas that are climatically suitable now for lodgepole pine versus the 2060s, you see a significant decline in the climate suitability for things like lodgepole pine. So I'll just go back and forth a couple of times so you can see how that shifts.
Do you have
Yeah.
pre-1750 characterizations of the ecosystem? So layer that?
I'm sorry,
To show those three?
you know, I'd have to ask that of Jeremy Littell, who actually will be coming, do you know when Jeremy's scheduled?
In either October or November.
October or November, Jeremy's going to be coming and getting into the forest impacts in much greater detail. So he's done a lot of paleo work, looking at how stream flows, for example, have changed in the Columbia Basin as a result, using core data from trees and tree rings, for example. So he's got a good sense of how things may have changed over the last 500 years or so in the basin and in the Northwest. As I mentioned, risk of fire increases, and historically, the historical average for area burned is about 425,000 acres, and we see that that average moves up as we move forward in time as areas dry out and as more areas are affected by things like the pine beetle, to the point that by the 2040s we could expect the average area burned to be about 1.1 million, and by the 2080s to be about 2 million acres. The probability of a fire being greater than 2 million acres in any given year also goes up. So historically it's about 5%. By the 2040s, that probability increases to 17%, so about a 1 in 6 chance. The 2080s, the statistic is very high, 47%. And Jeremy will point out that at this point, by the 2080s, you have to wonder if there's enough area left to burn to get fires of this size. So this statistic probably goes with the caveat that there just may not be enough area left to burn at that point. But it certainly gives you an indication of the direction that we're headed towards.
Any ideas about what species will be infilling these areas, like dead trees?
That's the magical question. Yeah, that's something I think a lot of people would like to know, particularly in the sense of trying to anticipate how, as areas get logged or whatnot, what kind of more drought-tolerant species you might want to plant. And I don't think we have a good question on that yet at this point. That'd be a good question to talk to Jeremy about. Perhaps he'll have some more insights on that. I mean, I know he would. But, was there another question? Okay. So these changes in forest cover and changes in grasslands, whatnot, because of fire and other disturbances will certainly affect species. And this is looking at some work by Josh Lawler at the University of Washington, where he has actually developed a database of more than 3,000 species, or is in the process of compiling this database of 3,000 species that shows how their habitat ranges may change as a result of climate change modeling, looking specifically at one climate model that had CO3 and one scenario, the A1B. Now, to put this in perspective, we looked at 20 climate models and 2 emission scenarios for doing the hydrologic modeling work and the temperature and the precip projections. This is looking at one model. So there are other models may produce different results, but this gives you an idea, at least under this scenario, how the range for the northern goshawk may change. And while it's hard to see, this is the best resolution we had, because this is actually modeling for the North and South America. You do see a contraction of the range in the Pacific Northwest with an expansion in Upper Canada. And actually, you know, as I mentioned, Josh is aggregating this for 3,000 species, and, you know, if you just kind of blur your eyes, you can see the changes on the order of about 10 to 20%, some areas in that 20 to 30% range, species turnover in the Northwest. This doesn't mean loss of species, just means a shift in the types of species that may be found in the Northwest. And looking at individual species like the pika, thank you. I just have some kind of a block about that. Jeff Hickey is at the University of Idaho, has done some work along with Jeremy Littell and others in our group looking at how habitat for the pika and their range may change as a result of climate change. And what they see are decreases in the range of 81 to 98% as a result of primarily the changes in snowpack, which are important to pika for burrowing and other parts of their life stages.
What time frame is that?
This is, that's a good question. I will have to look at my notes. I don't know. Thank you for pointing that out. I just integrated this in because I just got this information recently, and it's actually based on work that's currently being submitted. So I'll have to look and see what that time frame is. I would guess mid-century, but yeah. If we look at coastal and marine environments, sea level rise is, of course, the dominant driver in coastal and aquatic environments. And when we look at the global drivers of sea level rise, we see that thermal expansion is a major contributor. In fact, most of the sea level rise that's been observed to date comes from thermal expansion. So as ocean water gets warmer, it takes up more space, and you can replicate this in your own kitchen by filling up a pot near to the brim, put it on your stove, turn it on medium, but don't bring it to an active boil, and let it sit, and as it warms up, it will eventually spill over just because it physically takes up more space. Also, melting of land-based ice, so things like Greenland and Antarctica. As those ice sheets melt, they do contribute to sea level rise. The IPCC projects globally a rate of an increase in the range of 7 to 23 inches. It's a range just like you saw for temperature, because it's being driven by some of these same assumptions about how future greenhouse gas concentrations in the atmosphere will change, and as a result of how temperatures may change. Regionally, if we start looking at that, as we start looking at the global change at a more local level, there are other factors that can affect sea level rise in any given location. One is atmospheric dynamics, which is another way of saying things like wind-driven pileup of waves along the shore. So, for example, during El Nino years, because of changes in wind patterns and circulation, we see that average annual winter sea level along the coast is actually around 8 to 12 inches higher than normal. And that's because El Nino tends to change the winds in a way that the winds are blowing onshore and pushing the waves up along the coast. So if climate change were to affect those wind patterns in a way that made that a more persistent pattern and not just something that occurs during El Ninos, that would contribute to higher sea level rise regionally. Of course, conversely, if those wind patterns are shifted in a way that they're blowing more offshore, it pulls waves away from the coast, so perhaps we actually don't see as much as we project globally. Tectonic processes are also another major factor in assessing how sea level rise will change at any given location. So we live in an area where plates are subsiding and uplifting, and that's happening at varying rates around the state, and that will in some ways offset or exacerbate the projected sea level rise at the global scale. So taking those into account, we have looked at sea level rise for Washington State, and medium estimates by 2100 put sea level rise of about 2 inches for the Northwest Olympic Peninsula. And that is because the Northwest Olympic Peninsula is an area where there are different data sets in agreement that that area is uplifting as a result of plate tectonics, and it's uplifting at a rate that is about even with the projected rate and sea level rise until you get to the end of the century, where sea level rise eventually outpaces the projected uplift. For the central and southern Washington coast, projecting a sea level rise of about 11 inches. This is, again, a medium estimate. And then 13 inches for Puget Sound. We can't rule out higher values, particularly if Greenland and Antarctica contribute more globally than the IPCC factored in. And some of you may be aware that that was a criticism of the IPCC's estimates, that they did not factor in enough change from Greenland and Antarctica. So if we assume kind of a worst case scenario for this century where Greenland and Antarctica continue to contribute significant rates of melt and therefore sea level or water into the ocean, we could see up to 4 feet of sea level rise in Puget Sound. It's considered a very low probability, but we can't say it's a 0 probability. So based on the risk tolerance of the individual decision maker and what you anticipate the lifespan of a decision to be, for some people, knowing that upper range of up to 4 feet is important. For other people, planning for 13 inches is fine. Now, increased storm surge and episodic flooding will actually present more of a challenge in Washington State than kind of this slow inundation associated with these projected changes here. And that's what we kind of associate. You know, from Al Gore's An Inconvenient Truth, you know, you should see the picture of Florida half submerged. And, you know, there's this notion that with sea level rise of X many inches, you know, it's just like filling up the bathtub 2 inches higher, and it seems fairly benign. But the problem is these big storm events that come through. So that actually happen on top of higher rates of sea level, or happen on top of higher sea level. Sorry, I should have had more caffeine this morning. Hugh Shipman at the Department of Ecology has some interesting statistics that with 1 foot of sea level rise, a 100-year flood event in the Puget Sound region goes from being a 1 to 100-year event to a 1 in 10-year event, meaning it goes from having a 1% chance of occurring in any year to a 10% chance of occurring in any year. All right. A 2-foot sea level rise turns a 100-year event into an annual event. So it takes it from a 1% chance event to an annual event. And it's responding to these kinds of events that's really going to drive our response to sea level along the coast. You know, this happens and then the emergency permits come in, emergency requests for permits, and the state has to respond. Now, what does 2 feet of sea level rise look like? Well, we got a nice sneak preview of it just this past January. As many of you may recall, we had record high tides in January and early February because of an extremely low pressure system that was sitting off of the west coast. And when you get a low pressure system in, it essentially lightens the weight of the atmosphere on the water so that the water expands. So we had high tides that were 2 feet above the predicted tide level. This is what it looked like at Alki Beach, actually a photo from you. And you know, there are steps down here to a beach somewhere. And the water is coming through these gaps, the drain pipes, in the wall. A very nice placid-looking picture, but you can imagine if we'd had a storm that came in at that same time, we would not have pictures like that. We would have seen pictures more like that. So we were very fortunate, but it was an interesting kind of a sneak preview of what a 2-foot sea level rise may look like on a quiet day. With the increases in sea level rise, there will be changes in the types of habitat along the coast, and these are statistics from a report done by the National Wildlife Federation in 2007, where you see losses in estuarine beaches, tidal swamps, tidal flats, and a conversion of brackish marsh into some of these other types of habitat. The big issue, of course, is will these habitats have the ability to adapt? Will they be able to move back as sea level rises, or will they be squeezed out? And in some areas, they will be squeezed out. There's no getting around that. In other areas, there may be room to allow them to move back. And those are some of the decisions that the state is having to make and local governments are having to make as they move forward and thinking about the implications of sea level rise for the coastline. Once you get into the water, ocean acidification is a big question mark, and its implications for the ocean food web are potentially significant. So the ocean has absorbed an incredible amount of the carbon dioxide that we put into the atmosphere over the past 250 years. And because of that, we've actually seen less warming than we would have expected just from the straight physical input of that CO2 into the atmosphere. But as it's absorbed that CO2, it's changing the chemistry of the ocean. It's becoming more acidic. It's changed 0.1 units since 1750. And some of the most acidified waters are actually off the west coast of North America. And that has to do with the bathymetry, or basically the terrain of the coastline, where we have the shelf that drops off, so you get deep upwelling of cold waters up to the surface. And also because of the cold water temperature, which enhances the chemistry that contributes, that's related to ocean acidification. And what happens is that as a result of acidification, the organisms that form shells, or things like corals, become more brittle. Those shells become more brittle and more calcified, or in more acidic water. So things like corals obviously are a very visible part of the ocean environment that can be affected by ocean acidification. But what's less visible, but potentially as or more significant, are impacts to plankton and zooplankton. Obviously, they form the base of the food web, so this has implications across the food web. The question, though, is whether these species can adapt, and that's an area of active research. Some zooplankton and phytoplankton clearly cannot. They clearly have weakened shells. Others seem to be able to adapt in lab. These are all in lab studies. But these are all very early. So it's yet to be known exactly how something like ocean acidification affects a broader ecosystem. It is one of the things that is suspected in contributing to the decline of natural seeding for the bivalves in Washington State. That's one of the theories that they're looking into, that the ocean acidification that's already been detected is affecting the ability of these bivalves to seed naturally. So that could be the canary in the coal mine, so to speak. So I've gone across a wide variety of impacts. I know it's a lot to take in, but just to conclude with some of the bigger picture issues, global and regional climate is changing, and these impacts are expected to accelerate in the coming decades. The major impact pathways are increasing temperatures, declining snowpack, shifts in stream flow timing, changes in disturbance regimes, particularly fire and insects and forest ecosystems, sea level rise, and possibly ocean acidification. I think it's pretty clear that it's going to have some major impacts. The question is, how broadly will that extend through ocean ecosystems? The other thing that's important to note is that the future is not going to present itself in a simple, predictable way. So just getting back to the point that I made earlier in the presentation, where I think in the past has been this notion that global warming or climate change means that every year is going to be warmer than the next. So when we get a cold year, suddenly climate change is over. You know, Washington, D.C. gets 2 feet of snow, and people are jumping up and down because climate change it can't possibly be happening. See, it just proves that it's all a bunch of wackos up there talking about this. And that's not going to be the case. We're going to continue to see natural variability play out as we have in the past. So just consider last year, the year before, it was actually kind of a normal, I think it was last year, it was a very normal winter. It felt like it was cold and rainy and just miserable, but it actually was pretty close to normal when you look at the statistics. But the problem is that for the years prior, we'd had unusual winters, we'd had warmer winters, so suddenly we get kind of a normal winter, but it seems like it's really cold, and even locally we saw people claiming that climate change was over. And then we have this year, which was, up until recently, a much warmer winter than normal with low snowpack. That doesn't mean that climate change has suddenly accelerated. The difference is 1 year was a La Nina year, which tends to lead to La Nina years tend to lead to cooler, wetter conditions in the Northwest. This year is an El Nino year, tends to lead to warmer, drier conditions in the Northwest. El Ninos and La Ninas play out on an annual cycle. We're going to continue to see those happening globally, even as we get this long-term warming trend that's going to evolve over the course of the coming decades. Also, the results here are projections, not predictions. So these numbers, the specific numbers will change over time. So the 2040s are projecting an increase in temperature of 3.2 degrees Fahrenheit. Next round of modeling, it may be 3.5, it may be 3.7, it may be 3. These numbers, the specifics are going to change, but the trajectories of the change, we're very confident about those. We're very confident about projected warming. We're very confident about losses in snowpacks, about the shifts in stream flow timing. So it's important not to get too anchored to any one specific value and then assume because that value changes that somehow something is wrong or somehow the science was off. It's just an evolving science. And finally, I just want to point, obviously we know that the ecosystems are sensitive to changes in climate, as has been pointed out. Some of the things that really drive our sensitivity, it's the relatively low elevation of the Cascades to, say, the Rockies. These are two different mountain systems, really. The relatively low elevation of the Cascades makes us very sensitive to the warming that's projected, as you saw from the shifts in stream flow, or the shifts in basin types to the largely rain-dominant and transient basins. And also the presence of multiple stresses in a lot of these ecosystems. So when you look at things like salmon, climate change is going to be a stressor for many salmon species, but it's not just climate change that's stressing salmon. It's also habitat loss, pollution, and a number of other factors. So it's the accumulation of these stresses that ultimately contribute to how any individual species or any individual ecosystem responds to climate change. It can become the proverbial straw that broke the camel's back in many cases. It's not the only driver of change and stress in these systems. So with that, I certainly invite you to visit our website. I have a link here for the Washington assessment if you are interested in looking at specifically some of those chapters. We have a lot of published papers that you can see on our website that you can email us if you're interested in receiving any copies of those. And you're certainly welcome to email me at any time if a question comes up and you need some more information on anything presented here or just anything that you have a question about in the future, regardless of whether it was covered here or not. And my website, my email is lwb123@uw.edu. You can get it off the website. And any of our researchers, we're all listed on the website. So I thank you very much.
Do you have time?
Yeah, I've got, yeah.
So maybe open it up to about 5 minutes of questions, and then we'll wrap it up for today, and I'll let you know about next month's event.
As the glaciers are melting, Antarctica accelerates Greenland. Does that cold water cool the ocean enough that it makes a difference?
No, it doesn't. It may just locally, it might, just in the immediate areas around there. The thing that's discussed the most about those contributions are changes in salinity. So when you get large pulses of fresh water running off from the melting of these ice sheets, you actually change the salinity of the ocean in those areas around Antarctica and around Greenland. And that's contributed, that becomes part of this notion of the Thermohaline Circulation shutting down, which is, if anybody has seen The Day After Tomorrow, or is that what, yeah, it's The Day After, yeah, The Day After Tomorrow, which was a terrible movie from a few years ago that, it had about 3 nuggets of truth surrounded by, 97 nuggets of complete Hollywood dramatization. But the notion of the thermohaline circulation is that there is this kind of conveyor belt of ocean currents globally that brings warm waters up from the tropics up through for example, in the northern Atlantic near Europe, and that's one of the reasons why northern Europe is not as cold as it should be, because of these warm currents that come up and provide essentially heat to Europe. And what happens is they get up north by Greenland, the water starts to cool off, and the salinity changes and it drops. And so the colder, more saline water sinks, and it creates this push that drives this belt. So when you get large influxes of water from Greenland, and you get more fresh water coming in that affects that salinity mix, that's what contributes to the shutdown of the thermohaline circulation, because you don't get the sinking of the saline water. And that would actually lead to cooler conditions in Europe if it were to shut down. So we talk about the potential of a little ice age happening in Europe as a result of climate change, one of the ironies. That is, the whole notion of the circulation slowing down or shutting down is considered extremely low probability. It makes for some dramatic headlines, and the news really likes to grab onto it about it, but it's extremely low probability to the point that it's not really even discussed that much as a consequence of climate change. But it's out there. I mean, we can't rule it out, but it is out there.
So if they were to stop contributing, well, I guess my question is, what needs to happen to turn your projections around?
So that's the unfortunate part of the flywheel that we're on right now, is that if we were to stop all greenhouse gas emissions tomorrow, we would still see warming through the end of the 21st century. In fact, I can pull up that slide. There actually, when I showed the temperature projections, there is a scenario in those global temperature projections that shows just that. So this orange line down here shows the warming that would result if we stopped all greenhouse gas emissions and got concentrations at year 2000 levels. And we would still see 1 degree Fahrenheit of warming in the 21st century. And that's if we got the concentrations capped at year 2000, which is not going to happen. It would take on the order of a couple centuries for greenhouse gas emissions to stabilize and for temperatures to start declining if we were to stop all greenhouse gas emissions effectively now. And there's actually some good information in the IPCC reports where they've modeled out that trajectory. So you get this, there's this whole lag effect. And part of this is because of the resonance time of the greenhouse gas concentrations once they're in the atmosphere. So an individual molecule of carbon dioxide, once it's in the atmosphere, is in the atmosphere on average about 100 years. Some components of it are actually in the atmosphere much longer than that. An individual molecule of methane is in the atmosphere about 8 to 12 years, and an individual molecule of nitrous oxide is in the atmosphere about 120 years. You start looking at some of the man-made compounds that also act as greenhouse gases. Some of them can be in the atmosphere at the extreme end for greater than 50,000 years. So once they are in the atmosphere, it takes time for them to either be absorbed by natural processes or to be broken down by incoming ultraviolet radiation. So they don't just go out just like that. So it's this lag time that has committed us to warming through at least the end of the 21st century. So what has to happen is that we have to stop the greenhouse gas emissions, then you have to have time for the concentrations in the atmosphere to stabilize. After that, temperatures will stabilize, and then in the order of many centuries to a millennia later, sea level will stabilize, because the sea level rise response is much slower than the temperature responses. So it doesn't, I don't say that to make it sound like we should not be mitigating, that these efforts to mitigate are going to have an impact. They have a huge impact on how much warming we're expecting to see and the kind of impacts. I mean, we could wind up down here, which is still going to present some challenges, but it's going to present far lesser challenges than if we wind up here or above that. So it's now, we're not at a question of if we warm, but how much we're going to warm and what are those impacts. So there's a huge need to both mitigate mitigate greenhouse gas emissions, and to adapt to the impacts of climate change.
There are a couple more questions, but to be mindful of folks' lunch. I'm going to wrap it up, and then would you mind staying
Yeah.
for an extra? We actually have the room reserved for an extra hour so that folks can stay and talk both with Lara for as long as she's willing to be here and with one another. There's tremendous information. Thank you so much that's been shared today. It's an opportunity. We're hoping that these speaker series to go back to the strategic plan, look at some of the goals that we've outlined in the strategic plan. How can we start to integrate the science that we're fortunate to have for our region into the activities of our day-to-day work, and how can we really start to think creatively about addressing those strategic plan goals. So on that note, next month, June 9th, we're going to have an overview. We have the overview of the science. Next month is an overview of the policy. Washington State is a leader in climate policy, and there's still, as I'm sure a lot of us would agree, there's a lot of room to improve. So we're going to give a presentation on what policies are currently in place, how is that impacting our agencies' activities, and where could we go with regard to policy into the future. So let's give Lara one last round, and then